Hello, welcome. This is module CM4269 and it's the lecture on catalysts. There will be probably 2 or 3 parts to this as it's quite large, but we'll see how we go, and I'm going to try and go as quickly as possible, which we'll see what happens. Okay, so where we're planning to go this session or this lecture is through this. We'll think of catalyst types. Heterogeneous and homogeneous are the 2 big divisions. Then we'll look at phase transfer catalysts, biocatalysts and photocatalysts. Particular reading: Lancaster chapters 4 and 9 and Fogler chapter 10. There are other texts and I'll mention them on the way as usual on the slides. Right, okay, so where are we now? We're somewhere down in the middle here with the red box. And again, this is every lecture and we're firmly into green chemistry here. We're not messing around with anything environmental or the such like. Okay, so basic stuff. What is a catalyst? I'll be quiet and let you read these. The definition I like most is this one. It changes the rate of attainment of chemical equilibrium without itself being consumed in the process. Now, that's not no definition will be a catch-all definition, because in fact, as we'll see, catalysts do get changed or consumed, although maybe not in the sense that this definition means. But in green chemistry terms, they're spectacular, because what they actually do is they generally give less waste. They generally help the reaction go faster. I know there are inhibitors which make the reaction go slower, which also have application, but mostly I'll be talking about catalysts. They usually result in lower energy requirements. They are almost always better than stoichiometric reagents. But there are always buts. Some catalysts are really rather nasty. They're poisonous or maybe environmentally toxic, maybe heavy metal based, and so on and so forth. Okay, so back to basics. The sort of thing you all learnt when you were little baby boys and girls in school. So we have a reaction, reactants to products, and this part of the graph from here to here is about thermodynamics. It's delta G, it's delta H, it's end of the universe stuff. This part of the graph above the line is kinetics. So if thermodynamics asks, can we get there? Kinetics asks, how fast can we get there? Okay, so the classic explanation for a catalyst is if we have a reaction, the blue line, obviously the energy of the reactants increases until you get to a col or peak, usually the domain of the reaction complex, at which point the reaction moves beyond the point of no return and crashes down to products. And obviously the products are at a lower energy than the reactants because the products are more stable. That is the reason the reaction occurs. With the same reaction adding a catalyst, then in fact rather than the blue curve you follow the red curve. The activation energy is much lower, which means that the rate of the reaction is much faster, because the height of this activation energy is what determines the rate of the reaction. The higher the activation energy, the slower the reaction. And the modus operandi of the catalyst can be different in case by case, but usually it either facilitates or helps the reaction stabilize the reaction complex in some way, and we'll talk about that in more detail a little later. So, in terms of green chemistry, catalysts are the passport to lower energy costs, increase throughputs, and hence should be and are a major tool of green chemistry, and in fact of business generally. If you're in business, it doesn't matter if you're what colour you are, green leaning or sort of totally anti-environmental, it doesn't matter. Your business is about making money, and catalysts are one way to do that. Okay, you are very familiar with this. I'm not going to spend any time here. If I wanted you to write down the Arrhenius equation, K equals AE minus the activation energy divided by RT, I'm sure you could do that, and I'm sure that you have used that type of approach often in the past. Okay, so there are two great splits in the catalyst world. One is heterogeneous catalysts, and one are homogeneous catalysts. They are different, and they have different advantages. So with heterogeneous catalysts, they're in a separate phase by definition. Heterogeneous, you can filter them out, they're easily separable. But there are disadvantages. You have diffusion control, you have other rate determining processes apart from the chemistry. The homogeneous, of course, they don't have diffusion issues because they're spread right throughout the reaction mixture. But of course, then you have to get them out afterwards, especially if they're fairly nasty. So, this table is from the course booklet, Manahan, and I won't read it. Here's a comparison of heterogeneous and homogeneous catalysts. We're going to start with heterogeneous in this lecture. Okay, so we've looked at the differences briefly. Why do we have to choose? I said quite carefully the two types of catalysts have different types of advantages. Now that is actually a good question, why choose? We'll see later on that actually there have been quite a lot of quite successful efforts to get some of the advantages of homogeneous catalysts into a heterogeneous format so they can be recovered more easily. They're called supported homogeneous catalysts, and we'll deal with them more a little later. What are the broad types of heterogeneous catalyst? We've got so-called asymmetric catalysts, biocatalysts, phase transfer catalysts, and photocatalysts. And these are, if you want to, where we're going to go. First, let's think of get the model clearly in our head. We have a reaction mixture with our solid heterogeneous catalyst particles in it. Now, I think you've handled the theory of what I'm about to talk about in the second year, but nonetheless, let's do it briefly. Before a catalyst can be involved in any reaction, as the expression, the old English expression is, the dog has to see the rabbit. That means the reagents have to get to the catalyst. So, first of all, the first stage is diffusion to the surface. Then, most heterogeneous catalysts, in fact almost all, have pores and very high surface area to allow greater reactivity and availability of reaction sites. So after the catalyst has diffused to the surface, it then diffuses into the pore. It then physisorbs, that's physical absorption, it's van der Waals forces, it's not chemistry particularly. And once it's physisorbed, it then becomes mobile over the surface. At some point, when it gets to a particular reactive center maybe, that physisorption becomes chemisorption, so then a chemical bond is formed. There's more surface diffusion, at which point maybe two of the surface moieties meet, or two different surface moieties meet. There is reaction, there is then desorption out of the pore and off from the surface. Okay, that's a fairly general model, but that's a fairly good description of the catalytic cycle. And in words, the next few slides talk about those, so I won't talk about them anymore now. Physisorption and chemisorption are not normally rate determining, especially because you can arrange the conditions, the flows and regimes to make them non-rate determining. So you stir it so you don't have very large diffusion gradients toward the catalyst and such like. Okay, the reaction, once the reagents are absorbed, then reaction needs to occur. This is usually the rate determining step. After reaction, the products then dissolve from the surface. Okay, so catalysts, we had this fantasy when we were little boys and girls. We were told catalysts are unchanging, eternal, they go on forever. Well, the bad news is they're not, and the worst news is they're really not. Catalysts undergo poisoning and undergo deactivation, and unfortunately these two processes are both inevitable and usually fast, and of course they're increased by the number of moles of reaction that you're moving through the catalysts. There are 5 main causes. Poisoning is usually defined as strong chemisorption of a species which you're not interested in. Sulfur in oil, for instance, is one. On the active sites, you're interested in dealing with the oil, but actually the sulfur absorbs on the active site and bungs it up. Impurities in the feed is usually the source of these. Formation of deposits on the catalyst, either by simple deposition, which is called fouling, or catalytic or thermal transformation of the feed components. So effectively in the second case, the catalyst is working. Unfortunately, it's coking up with the products at the same time. Chemical and structural alterations of the catalyst. So typically when you have poisoning or impurities absorbed, that allows or can allow different reactions, particularly reactions to do with the catalyst structure per se. So noble metal sintering by sulfur poisoning, for instance, dealuminization, collapse of zeolite structures, and so on and so forth. The other remaining 2 causes, mechanical alterations. If you're stirring this stuff round, for instance in a liquid environment, mechanical stresses, the particles crashing in, attrition, abrasion and erosion. Or the other common thing in liquids anyway is the leaching of the active species from the catalyst. two problems. A, it goes into either the waste or the products, and usually it's valuable, and B, your catalyst stops working or stops being as efficient. So, what can we do about this? Well, there's two or three things, and our first major part of this lecture is going to be actually zeolites, and so we're sort of slowly drifting toward them. The first thing we can do is reactivation. Now, rejuvenation is reactivation that can be carried out in the reactor in conditions which are pretty similar to their operating conditions. So, for instance, if you've got, I don't know, non-polyaromatic carbonaceous compounds deposited under mild conditions and low temperatures, maybe on hydroprocessing catalysts, you can run the rig at a slightly higher temperature, maybe increase the flow rate slightly, and or the hydrogen flow rate, and you can clean the catalyst, rejuvenate the catalyst in situ, no problem. And it won't surprise you that rejuvenation is one of the regular parts of using a catalyst, and in typical oil refineries it's not done once a year, it's part of a daily routine. Okay, unfortunately that doesn't solve all of our problems, and even rejuvenation is usually not complete rejuvenation. There are a limited number of cycles which you can clean catalysts before you begin to affect their activity. Regeneration is the next most severe treatment, and that can be carried out either in situ, that is still in the plant, or you take it out and treat it under different conditions, or you replace it and treat it, or whatever. So effectively, coking, sintering, they're typical examples of deactivation processes which are irreversible under your normal process conditions. So both are carried out in an oxidative atmosphere, which is obviously entirely incompatible with the catalytic transformations that you're going to be doing in a refinery. So these types of catalysts need reactivation after one or many reaction cycles. As I said, we're heading towards zeolites, and typically regeneration will usually regenerate the surface hydroxide part of the catalyst, which as we'll see is for them one of the most important parts. How do you judge a catalyst? Selectivity. I won't read it. Basically, that it produces what you want, your desired product, with very few byproducts. Turnover frequency. How many moles of product can you produce per mole of catalyst per time? It's also defined as potency. So low potency, you have to use high amounts of catalyst with therefore higher costs. Turnover number, the amount of product produced per mole of catalyst, and it's related to the lifetime. And this is about costs and waste. So they're the three criteria by which you judge catalysts. This has so far been fairly general, so what we're now going to do is move on to the first major class of catalysts, which are called zeolites. Okay, I'll just let you read that for a moment. Okay, so zeolites are an extended silicate aluminate structure, and they're linked together by shared oxygen atoms. They are naturally formed by heating and hydration, and there's about 45 natural zeolites formed by the geological cycle. However, they're not the main source of the zeolites we use in the chemical industry. Mostly we synthesize our own zeolites because they can be made much more consistent than their wild brethren. And if you're making it yourself, you can introduce other metals in, apart from just aluminium, or which gives you different reactivity or specific reactivity for specific applications. Okay, what I'm going to do now is show you a picture. Okay, this is a representation of a zeolite structure, or the way they're put together, which actually helps you understand something about them. So here is your silicate structure, and of course these oxygen atoms are shared then with an aluminate or another silicate, depending on what the structure is. These are usually, the primary structure is usually described like that, and so maybe you might have two together, or they might be arranged as a cage or a ring or such like. The variety is actually quite massive. So these are all zeolites. They have a naming structure, a naming system we'll talk about in a moment. And what I want you to notice is you've got lots of holes, lots of reaction spaces, cages, and this is why, or one of the reasons, why zeolites are so useful. We'll come back to this slide in a moment. So, their usefulness hinges around certain properties. There are various very well defined in zeolites micropores and macropores, normally defined by those types of ring structures we just saw, with multiple size entrances and exits. There's a high external surface area, and because of all the oxygen, they're actually hydrated. So you have a Bronsted acidity, which is a very important property in terms of the action and way you can use these substances. The defining feature of zeolites is their frameworks are made up of 4 connected networks of atoms. I just showed you the tetrahedra type way of thinking about it, with a silicon atom in the middle, an oxygen atom at the corners. Then these tetrahedra can link together by their corners, and there are a variety of structures, and again I'll show you a few more in a moment. This framework structure may contain linked cages, cavities, channels, and of course they're of different sizes but consistent sizes. So this means that they become molecular channels, places where certain molecules only can fit. Now the type of range you've got here is typically between 0.3 and 20 angstroms in diameter. So that's a good size if you're working as a mechanistic chemist. Now, I said already that most of these are synthesized. They come in many structures, many aperture sizes, and hence there are very many applications. And of course they are designed for certain applications. So you design your zeolite for particular ring sizes to accommodate particular reactions. And the structure can host quite a large variety of cations. Think of the natural geological system, the granites and things like that, and the clays. So sodium, potassium, so the alkali metals, alkali earth metals, and other more exotics. And they're loosely held, which means they can be ion exchanged. And again, we'll talk about that more in a moment. Okay, this loosely bound metal ions because they're loosely bound, they can be replaced with hydrogen ion. So you can program the acidity in the pores. You can think of it either as an H plus source or H plus, whichever you prefer. But that is one of the factors you can engineer in those reaction spaces, and here's an example, where you want to do your reaction. So this type of, it's a sodalite cage. Each of these, if you like, are a little mini cage, and so there are holes, there are ways into it, and you can have programmed acidity inside it. So you can have reactions occurring in there and going from one cage to another through like a channel, if you wish. But these are arranged in such a way in 3 dimensions that you have a large cavity, a so-called super cage in the middle. Now, there are a number of types of sites. There are so-called type 1 sites, type 2 sites, and type 3 sites, depending on where they are in the structure, and more a little later. We thought, showing you a structure here, I'd like now to think a little bit about nomenclature, because we're going to need to go there anyway at some point. So, the general types of zeolite. So we have a whole range here with typical oxide formulas. M obviously is your alkali or alkaline earth cation. N is the valency of the cation. I'll let you read that. There's no need for me to read it. But remember what I said about being designed for certain pore sizes or certain applications. Okay, this table here is synthetic zeolites, and there's a reference here, a very boring reference, but it's all about nomenclature. We've talked already about primary building units, the silicate or the aluminate, PBUs, and they are put together into secondary building units. We talked about size and names and description. So link 4 tetrahedra together, you end up with a 4 oxygen ring. If you think about linking 4 tetrahedra to this one here. And typically your shorthand will be S4R. You can see how this works. 5, 8, and so on and so forth. There's some subtleties in the structure. Single rings or double ring, single or double or rings, which we'll look at in a moment. Again, the reference is boring, but it's all there should you need it. Okay, here are some typical framework topologies. We looked at sodalite already, which is A, with its relatively small opening there. You can have a zeolite type structure, and again that's the AZK4 type zeolites, or the XY type zeolites, like that. And they're differentiated. They're all made up of sodalite cages, but they're assembled differently. Okay, what I'd like to do now is show you, go back to the slide we were looking at a moment ago, and look at a couple of other types of structure. Okay, so here are some of those structures, some examples, and if you like, these are a slightly different way of drawing them when you're trying to show the, if you like, the backbones of the structure. So the holes here are actually going from left to right through this structure. So very, very useful for catalytic type applications. But I said you could actually synthesize them so that you can program the pore size. For each of these, you can now see the distributions of pore sizes of these different substances. So you've got a couple of zeolite Y's there. So you've got for your zeolite Y, you have your cage size, your pore size there. For your the other form of zeolite Y, you have it there looking at the different pores, and so on and so forth. So you can see the pore size here ranges from very small, which is about 0.5, 0.3 I think is the minimum, up to 1. In fact, it can go a lot higher than that, depending on the architecture that you choose to use. This is one of the zeolite workhorses we're going to talk about quite a lot, ZMS5. And you can see very clearly in this structure the types of apertures. It's a quite small aperture zeolite, about 0.6 nanometers, which means that larger molecules are excluded from it, which means you can control what reactions occur in these tunnels, in these cages. Okay, so the catalytic performance of these things we're going to look at in a lot of detail in a moment. But before we go there, we should first think of the non-catalytic applications, because there are quite a few. The most obvious one is in wastewater cleanup. Zeolites are very, very useful because of this pore structure. You can get processes, pH controlled processes, occurring in the pores, and they're widely used as wastewater cleanup. Catalysts isn't correct because they're not acting as catalysts, they're just acting as reaction sites. Detergent builders is another, and there are quite a few others. Anyway, this lecture is about catalysts, so let's really start going in that direction. So, good catalytic example for zeolites is fluidized catalytic cracking. It's refining of fossil fuels. Typically, the whole thing is in a fluidized bed, and we talked about fluidized beds in the last lecture. The catalyst is present as 60 to 100 micron particles, and they're suspended by the liquid flow. Remember that FCC doesn't crack N less than 7, so petrol goes straight through. The advantages of this fluidized catalytic cracking. Remember we talked in the last lecture about thermal cracking, that free radical type mechanism. Well, this isn't. It's a carbocation mechanism, so it's cleaner. And I'll show you in a second how important the H plus is in zeolites to this mechanism. Okay, so here is the reaction scheme for this, and you can see what's happening. Why H plus is so important, because it's coming from the zeolite, which also tells you why the catalyst will get exhausted at some point. Anyhow, and so effectively you're going via carbocations. You'll remember the most stable carbocation is the tertiary type carbocation, and you can see the reaction process moves as described. So a lot more efficient, a lot less random than the old thermal system. Let's look a bit more closely at this type of fluidized catalytic cracking. So typically you might use zeolite Y. That's a synthetic fugicide. You can look that up if you want to. Relatively large pore size, maybe 0.8 nanometers. Got an open structure, allows quite large hydrocarbon molecules to enter the pores. But the highly branched ones won't get in at all because it's too small for that. There are obviously coking issues here. If you want to make this even better, what's typically used is take about 15% of the sodium in there and replace it with lanthanum. Partially fluorinate it, that increases the acidity further, and effectively also gives you smaller aperture increases, which actually makes the thing more effective. Remember, petrol goes straight through, so it doesn't reduce the octane value, and that's a typical example of how you might use a zeolite in that process, or rather the tweaks to make it really effective. I talked a moment ago about how, particularly with zeolite Y and this sort of heavy duty stuff, coke formation is a important thing. Well, routine decoking always also allows the recovery of sulfur as H2S. I would be interested in sulfur, wouldn't I? And that can be sold, which is great, and it reduces sulfur oxide emissions, yeah, there you go. This ongoing routine decoking has to happen regularly, but every year or so you go for a complete shutdown, which allows complete replacement or total regeneration of the catalyst, rather than doing it in situ is limited. Basically, you don't solve all the problems that way. Okay, let's give you another example. Zeolite XSM5, if you looked at the picture earlier, is used to convert methanol and benzene to p-xylene because the pores allow the entrance of only one size of molecule, which is quite interesting. And this little diagram gives you some idea of how doesn't allow multiple branched, so you don't get O-xylene, you don't get M-xylene, but you end up only with p-xylene. And of course all of these are reactive surfaces, so the molecule is reacted on the way through. Okay, so an aside, I suppose, in one sense, methanol, bioproduced via syngas, and ethanol actually, and routes into the green economy. Methanol is really important, required for fuel cells, or again using our old friend ZSM5, you can convert via the MTG process methanol to petrol. So really useful. Okay, let's give you a more chemical example now, and I'm going to give you the Asahi process. I can't say that properly. It's the route to nylon 6 and 6,6. It actually was the centre of the Flixborough disaster, but on our way there, because of the conditions that were required, I'm going to show you something about the issues with the stability of high acidity, high silicon zeolites, temperature, and this so-called water resistance. Okay, This is what you do not want to happen. Here is your zeolite under the old conditions of the process: 230 centigrade, 10 atmospheres oxygen, hydrocarbon, what a mixture, eh? High temperature oxygen, hydrocarbon, that was underlying Flixborough. But for this reaction, and incidentally only 6% per pass conversion, but under these conditions and this high temperature, the reaction of water with this zeolite can result in the breakup of the zeolite into collapse, which of course is just what you don't need. You don't need your catalyst to decompose on you. So the modern process, using 100 degrees centigrade, and again cyclohexane is the key intermediate. I'm not going to go into the chemistry, but at that lower temperature you can use ZMS5, can't say it, high silicon, high acidity, and successfully run that process without destroying your catalyst. I'm not going to keep going through all of these. It's simply useful to give you an idea of the range of catalytic processes that zeolites are involved in. This is an interesting one, quite recent process, the conversion of benzene to phenol using N2O as an oxidant. Really interesting. N2O is a greenhouse gas, and therefore you can actually recover it from air and use it as a reactant, and technically I suppose earn some carbon credits. This is the alpha ox process, and again it's our friend XSM5, but this time containing iron at about 300 centigrade, 30% per pass, and selectivity 99%. And I'll let you read this. Effectively, N2O dissociates on the catalyst, and the active oxygen atom reacts with benzene, which leads to your phenol species. It's a very neat little process. The only question is we still don't really know which site, which is the alpha site in one sense. What determines where the alpha sites are in the zeolite? It's thought to be the iron extra framework sites, because the iron is actually not in the formal structure. It could also be Lewis acid sites, although they would both be similar in that sense. Okay, so we've just thought about the alpha ox process where you had iron in there. This moves us toward another option you have to modify the zeolite framework by introducing d-electron source metals into active sites. This allows you to actually tailor-make catalysts. How might you do that? Well, how you might do it with acidic zeolites. Basically use some sort of complex like this with ammonia, allow it to equilibrate so that your platinum or palladium is fairly evenly distributed through the matrix. Then you calcine it under air and then hydrogen, and it gives you small platinum crystallites in less than 1 nanometer cages and tunnels. Very effective catalyst, allows you to do somewhat different things. Okay. Right. So these metal sites, the platinum sites, actually catalyzes reduction hydrogenation steps and rearrangement and cracking by the hydrogen site. So you've got an acid, start with an acidic zeolite, you've put these platinum crystallites in. Now you have a system which can do 2 or 3 different things, different processes at the 2 or 3 different sites. There's an exception here with N-hexane and benzene, where the platinum can catalyze both operations. This is a very light take on so-called ship-in bottle synthesis, where you tailor make your catalyst to such a degree that you actually you have complex, multiple and different functional active sites in different zeolite cages. There's a couple of examples here for you. Here we've got a lithium ytterbium zeolite containing manganese complex, which then allows you to do a hydrogen peroxide epoxidation of alkenes, and hydrogen peroxide, you know there's going to be radicals involved. Complex reaction, but you've got a number of different sites that steward that reaction right the way through. So I won't read you the summary. One of the real benefits of zeolites is they are so flexible, and you can do many useful things. Tailor make them to underpin many of the basic chemistries. Okay, I think that's the end of part 1. Bye bye.